let's get started. So today we are going to continue our discussion on Spark, and we are starting with the basics and foundations of Spark, and which we call the basic operations on RDD. So far in with respect to RDD, we have understood the basics of RDD, and we are making ourselves familiar by doing various operations. We have learned what it means by transformation and action. We also took a couple of examples in order to understand what is a transformation and what is an action. We're going to take a look at more examples of transformations and action, and that will make you more confident, and that will also help you solve the problems. So the way we are approaching the problem solving is that on one hand, let's say we want to solve the problem, and on the other hand is what does the technology provide to us. So we are starting from the what does technology provide to us, and once we are comfortable with what does Spark provide to us, then we will be able to solve the real practical problems. And while we're learning the technology, like while we're learning these operations provided by Spark, we'll be taking up small examples. They may not look very practical, but they will be um, part of a bigger practical problem. All right, so let's get started. Now, again, when we are working with Spark and RDD, the idea is that we should be able to process data that is unstructured or semi-structured, meaning the data that doesn't have columns, the data for which the columns have not yet been defined, we should be able to process such data. Such data could be plain text files. Such data could be in the form of videos or anything else. All right. So probably after this session, in the next session, I'll try to take up a completely different problem. Okay, let me just make a note of it. Image resizing problem using Spark. All right, so this we will introduce in this course, and all right, this project will be adding soon. Okay, so let me just give permission to record to Robin. All right, all right. So here, what we are learning is we are learning how to do transformations. There are some more transformation examples we want to take for Spark, and let's take a look at a transformation called union. Now, what is union? Imagine that we have an RDD called A, which is basically created from the memory array, the array in memory having 1, 2, 3, and we have another RDD B, which is again created from an in-memory array. We want to union them. Yes, this is exactly same as SQL union. All right. So please note that union does not remove the duplicates even in SQL. So yes. So when we say c.collect, we get the result. The records from A and records from B are concatenated together to give the outcome. All right. The link to the docs remain the same as the last time. Okay, so let me just give it again. So good. All right, so it doesn't remove the duplicates. All right, now, so essentially union is concatenating two RDDs into 1. Please note that after union, the C that you see here, this C is also another RDD. All right. So this is what union does. All right. Now the practical use case of union are many, and we will see some of them. Let's say we had some unstructured data from log files having the text files, as in the errors and debug messages, info, and so on. So so let's say we are creating two RDDs out of this the whole log files, and this RDD is just errors, and this RDD is just warnings. And we could do union both of them, error and warnings, and we'll get the bad lines. Now, this is a practical example of using union. So we could actually create two RDDs, one by filtering based on filtering by detecting which lines are error, and other by detecting which lines contain warnings, and ignoring rest of the lines, and then concatenating them. Okay, you might argue at this point that we could have done it in a single filter step. Yes, we could have done both of these without union. We could have just done it in a single filter step, but this one is quite useful because maybe we are just interested in errors or warnings. In that case, we can just use this or use this. All right, so this is far more modular, and the performance wise, it'll be equivalent. It'll be equivalent to combining these two filter statement into one. A question from Mohammed is that the filters could be contains errors and contains warnings. That's right. And then use flat map. Here we're just using filter, not flat map, because we don't want to change the definition of a record. We just want to let it be the way it was actually. So imagine the input RDD is just a bunch of lines out of which we are filtering some lines to create errors. So we're just using filter, and then we are using another filter, and then union on both of those. All right. And of course, every filter could be emulated by a flat map. All right. Now, we could save the results as we have already talked. We could save the results to a text file. Now, the next action that we talked earlier was basically collect. Collect brings all of the records to the local memory. So please remember that collect is a dangerous function to use. And if you let's say somebody calls you and says, hey, my Spark program is really not working well, it's very slow. Please take a look at the code and see how many times have we used these statements like collect, take, and other save as text file and load. So such statements are basically the collect is actually something that is bringing data out of Spark to the local memory, and hence it'll basically lead to either memory overflow or really slow down. So the only practical use of collect could be just for debugging purposes or just for display purposes. But in case of big data, we don't do that. All right. So we have to be careful to use collect. Collect brings all the records to the local memory. Right. The difference between collect and take is collect brings all the records, while take brings only some number of records to you. Okay, only few of them, whatever you specify. So if we know the length of the data, if we use the count and we get all the records, we get the total number of records, and we use that number with take, that then take is equivalent to collect. That's right. So, all right. So collect is nothing but take with all the argument or all the elements. Okay, so it brings back the data to the driver, and that could overflow the local memory. So you just use it with very much caution. And right now, next, when this one we have already talked about, the take only brings some of the elements. So here its take is only bringing 4. All right. So take is an action, collect is an action, save as text file is an action, count is an action. It counts how many elements are there in an RDD. Okay. Again, count works in a distributed fashion. It counts parallelly on all the machines. So imagine that you have an RDD having 3 elements on one partition, 4 elements on second partition, and the third partition is having 2 elements. So there are 3 partitions, first one having 3 elements, second one having 2 elements, and third one having 3 elements, right? So partition could be on different machines, running on different cores, and so on. So partition is the 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 unit of parallelization, meaning the only way to make it more parallelized is by changing partitions. We are going to discuss partitions in a little bit more details when we talk about optimizing Spark applications. So just that right now it is important to understand that what does it mean by partition. Every RDD has partitions, and by default Spark decides the partitions, and we can later on change the number of partitions. So here, the RDD is having 3 partitions. Now, when we say count, it asks all the partitions. It asks the machines or the or Spark application to start counting or parallelly on all the machines. Okay, and imagine that you have like three rooms full of the coins, and you need to count how many coins are there. So you will send 3 persons to all these 3 rooms to count the coins, and parallelly they are counting in the 3 rooms, and they return you the counts of the coins in each room, and you do the summation of all the coins, right? That's what count is doing. So if this one is taking 1 second, this one is taking 1 second, this one is taking 1 second, overall the time taken will be 1 second, not 3 seconds, because this will happen parallelly. All right.
Sandeep, my count should be 8. Why should be 7?
The my count should be 7, right? 3 plus 2 plus 2.
2 plus 2. You are counting the first element as 7 and then 3 also.
No, we are basically we how many elements are there in the first partition? 3, right? Second partition 2, third partition 2, right? So 3 plus 2 plus 2 is 7, correct?
Understanding is very.
No, 3 is the number of partitions. The other 3, if you the one which is outside the bracket is the number of partitions that
Okay.
he's counting as an element.
Yes. Oh, thank you, Sachin, for that. Thank you, Mohammed, for that. Yes. The last one is an interesting point that you have brought up. So when we are using, say, parallelize or sc.text file, there's always an argument which we have missed. There's a parameter that we can pass whereby we can enforce the number of partitions. All right. That we can specify number of partitions. So the last element that you see here is the number of partitions. Okay. If you don't provide, then it will basically, we are essentially explicitly telling Spark that, hey, we want 3 partitions. So please create 3 partitions, howsoever. All
Sandeep,
right.
I have a question on this.
Yes, go ahead, please.
Is it a good practice to give explicitly state the number of partitions, or it's like just go by the default?
Go by the default.
Just go by the
Okay.
default, don't explicitly state.
Yes, that's right. That's right.
Okay.
So,
Thank you.
yeah. So a good question at this point. So the number of partitions is generally decided by Spark. And the way the common practice is let the default partitions be the way it is. In the first pass, once you are done with writing your program and it's working fine, once it's working fine and things look okay, then in the next pass, what you do is you figure out that what is the point where we need to parallelize more or less. Because Sparky is making initial assumptions based on the amount of data, amount of cores available to you. Based on that, it is deciding the number of partitions by default. But you can definitely imagine that um, you have like petabytes of data, right? After doing the filter, you are left with only few records. Now, those few records, if they are spread across on, say, 50 partitions, it wouldn't make sense. So in those cases, we'll have to use our judgment in order to bring back or repartition our RDD, and we will do the deep dive at later point of time on the number of partitions. All right. So when we talk about optimizing your Spark applications, great set of questions. So more partitions means more transfer across the machines. More partitions would, let's say, if your data is on more partitions, then if you are saying say you are doing shuffle, or say you are doing the counts, there'll be more transfer involved in the network. So sometimes it might it might take more time than actually doing everything on a single machine. Like for example, the question that we have in here, if it was on single machine, it'll take a millisecond. But if it was on three different machines, the time it is going to take to actually contact any other machine is uh, is above 1 second. Therefore, unless the data is bigger, it doesn't make to do this. It doesn't make sense to do the distributed programming. Here we are just distributed 7 elements on three partitions. So it is not really a great idea. This we are doing just for the demonstration. All right. Because if you just for 5 6 record, if you are using multiple machines, it doesn't make sense. All right. It is actually really fast and easy to do that on a single machine. Very good question. So moving ahead, I hope that answers Sachin's question as well. And there was a question from Binta, how to distinguish between action and transformation. So do I have to memorize them one by one? Actually, the truth is you don't need to. You don't need to. And uh, when you are solving a problem, you will yourself um, be able to look at it and see that, okay, here whenever I'm calling this, it's returning you a local array. Therefore we should not be doing that, and you'll be able to do this. You don't need to memorize that this is called action, this is called transformation. As a matter of fact, I have done a decent amount of work with Spark, and I have not there are a couple of functions that I really don't know whether they are transformation and action. All right. So this is just extra information called action and transformation. We will more focus on individual functionalities provided on top of an RDD. Transformation and action is nice to know, but not really mandatory. Okay. All right. So it's not really needed to distinguish between action and transformation. While you're using that, you can quickly check if something is when you run a function and you see that it's immediately returning result and nothing is happening, that's generally a transformation. The thumb rule in case of Spark application is avoid the action till the last point. Okay, avoid the action till the last point. That's the thumb rule. Okay, do not let's say you have to do something. You have to say process some data, sort some data, eliminate some data, and transform some data or modify some records and update some files. Unless it's explicitly required, do not use an action. action should be saved till the last moment, just like while defining our SQL script, we press enter, or we press enter or run, click on run once our SQL script is done. In the same way, we don't call action in the midway. Okay, we try as much as possible, but because of our logic, sometimes we'll see that in future, that because of our logic, sometimes there is no other option than calling a collect, or calling a take, or calling save to HDFS. Because of logic, sometimes it becomes inevitable to call an action. All right.
Sandeep, I have a question on this.
Yes.
So you would call like an action to see if what result you were expecting.
Mhm.
So does the result match your expectations? I would say like it's like a print ln in like a print ln in Java.
That's right. That's right.
So for that purpose you may call, but maybe it's
So
just
save
to
as text,
verify.
yeah, save as text file also is an action.
All right, so
And
that's a better action than take or collect. So less memory overhead. That's why.
right, right. So
All
see,
right, great.
at the end of day, you want the job to save some data somewhere, correct? Or upload the data to a database or something like that. So for
Yes,
all of
yes.
that, you would like to use an action. Otherwise, for rest of it, you may not want to use an action unless it's explicitly required. Let's say there is some computation you are not able to do using map, flat map, or any other transformation, and you want that data to be locally available so that you can write a for loop, right? So there are many things that you cannot do in a distributed fashion. One of them is I'll give you a good example. Let us say that you want to do Fibonacci series. Fibonacci series is a good example. So Fibonacci, the series kind of things cannot be done in a distributed fashion because that's completely sequential. So those kind of things you might have to do local, and therefore in the midway you might have to say, okay, let me just collect the data, bring it locally, and then operate on locally, and then send it back to RDD, and then do the processing. Okay, so those are the scenarios in which you use the actions in the midway. And whenever you observe an action in the midway of your Spark script, then that's kind of making yourself alert that, hey, there's something wrong with his code, that why are we using an action in the midway? What's the point? This is something, because every time you call an action, it will basically bring back execute the entire job, bring back data to you, and when that happens, it is going to be, uh, the end of the job kind of thing,
So
right?
you use your distributed fashion. You use the, I mean, you lose the distributed architecture, right?
Eh,
Once you collect,
Correct,
that means
correct,
everything is coming back to your local machine. So there's no
exactly,
distributed computing happening.
exactly, exactly.
Thank you.
All right, great, great. So I'm really happy that we are going in that direction, in that direction of thought, that, and I would more emphasize on thinking in a distributed fashion, and that's why we will take similar more example where it questions our way of doing, our normal way of doing things, and that's exactly the objective of such classes, to make you think about our normal way of thinking, right? Remember our example of image resizing, where it took a while to realize that the three things could be done in parallel. So similarly, we will also question our other ways of doing things, and as we are moving ahead, you will observe that you will learn in the same fashion. All right. So good, good. Moving ahead, I hope this is clear to all of you. A question from Sachin is, if you don't give 3 as a partition, what will be the default partition? So Spark has its own way of deciding partitions. We will talk in more details. I'll give you a very quick brief on how does it decide on partitions. If the input data it is loading is using the parallelize function, meaning converting an in-memory object to the local one, it decides based on how many cores are available on the local machine. If it is running on Hadoop, then it decides it decides the number of based on number of cores available on the cluster for each job. So that's how it decides number of partitions if we use parallelize. If you're using sc.text file or any other similar function, if the file is on HDFS Hadoop, then it will decide the number of partitions based on sorry, it will decide the number of partitions based on the blocks in the HDFS file. Okay, because if you remember that a file in Hadoop is stored in the form of small chunks, and those chunks are called blocks. Those are fixed size blocks. The last block is generally smaller because not all the files are of the size which is multiple of 128 MB. Therefore, the so basically the blocks are decided based on the size of the file. So here by default sc.text file, if the file is an HDFS, the number of blocks that are decided, the number of partitions are decided based on the block size, based on the number of blocks in the file. If the data is in HDFS and we are running it on top of yarn. All right. I hope that answers your question, Sachin. Question from Hitendra: isn't save as text file almost same as collect? Correct. But the only difference is save as text file is saving the data to HDFS. It is little different because save as text file will parallelly save each partition to a separate file. If you have an RDD having 20 partitions and you are doing save as text file on that RDD, it'll create 20 files, one for each partitions in HDFS. All right. So save as text file would be slightly better than collect because collect is going to do two things. One is going to bring the entire data transferred to you to your local machine. Second, it's going to load it in the memory. Therefore, it's slower as well as it is going to overflow your local memory if the data is bigger, while save as text file will not.
I have a question on this. You
Yeah.
said like if you do like a save as text file, it would create the number of partitions equal to the number of files that will be there in HDFS, right? Like each
Yes,
partition will be a separate file. So
that's right.
won't that be like too convenient for you to combine everything together? It's
Yes,
like
so
very
you can,
hard to observe the results.
that's right. So your point is that save as text file should create, let's say, two files or one file of your
Yeah.
choice, correct? So
Yes.
what you can
Yes.
do is you can repartition your last step. You can say rdd.repartition, and then it'll have those many partitions, whatever you define, and then save as text file. So it'll bring down the number of partitions. All
Yeah,
right.
because it makes more sense to do that instead of having every partition as one file.
Okay. Okay, but interesting part is in a number of cases it doesn't. All right.
Okay.
So
Okay.
most of the data that we observe in case of big data, the data is going to be in number of files instead of one file, right? Multiple reasons. First one is that most of the data that comes in smaller, as in the files in there. So let's say for every day we are getting new data and we are put, instead of appending to the same file, we're going to put it in another file. So it is very common to have quite a few files in your folder. So there are many other techniques which you can use in order to collect and combine many files into a single file. One of them is by creating sequence file and so on. All right. So we'll talk about how to create sequence file and all, and we'll discuss that in details. All right. So that's why I want to take up this question on image resizing using Spark. Okay. All right. So it's very common to have many files in HDFS, and it's common to have many files as output, because in case you are just looking for a record, instead of scanning through entire files, entire data, you'll just scan through one small amount of data. So that's the objective. And more number of files generally lead to, um, basically, it's very common to have more number of files, though it's not very efficient to have many number of files. All right, good questions. All right, moving ahead. So this is how the count works. Great. So count is a distributed function, and just like any other thing in Spark, count is also distributed. So now we've talked about reduce. Was a reduce function when we talked about Scala's collections, right? We talked about reduce. Spark has more granular reduce functions. Okay, so reduce functions aggregate elements of an RDD. We have talked about various kinds of functions: filter, map, flat map, union. There is a function called reduce. Reduce is for combining the entire RDD into one. Just like count did. What did count do? Count basically did the counting of all the records in our RDD and gave you a single number. In the same way, in the same way, reduce can reduce the entire data set into a singular value. Imagine that it's not only for numbers. It can do the reduce for a huge RDD having say images, a big RDD having, let's say, strings. So reduce will aggregate the elements of in. So did I is everybody able to hear, or okay? All right, all right. So reduce can aggregate the elements of a data set using the user-defined function. Using a user-defined function. How does it do that? A question is that um, how will it combine the elements into single value given our function? So reduce function takes two arguments. The reduce function takes a function as argument, and that function that you're passing to reduce, that function takes two argument, and it returns only one. And this function that you're passing to reduce must be commutative and associative. I'll talk about commutative and associative very soon. It returns the return type of reduce, the function that you're passing should be same as the arguments. Both the arguments must be the same data type, and it should return exactly the same data type. So that's a limitation of reduce. How does it combine all the records that we're going to talk about now? Imagine that we have RDD created from in-memory array using parallelize. Now, let's say we have a function called sum. Sum is basically returning the addition of the two. Now, we could say sequence dot reduce and pass the function called sum as argument. And then we will get the results here. So here the important part is sum is taking two integers as the argument and returning an integer. If it was taking two strings as arguments and it was returning it was returning another, it would have to return another string. Imagine that in our case. So here take a couple of more examples. So here we're basically computing the total using the reduce. In the same way, we can compute max, min, and other things. And there are many things that cannot be done using reduce. The one that cannot be solved in this way. Let me give you more example. So here, this is what's going to happen when we run when we create sc.parallelize. It'll create the RDD which is a parallelized collection RDD, and then we defined a function called sum, and then we call that function via reduce. It'll give us the total. We can just quickly check whether it is right or wrong by using the standard formula n into n plus 1 by 2, and that's right, it is 5050. Okay, so that means it is returning correct. Now, how does the reduce work? How did it do the summation? Imagine that you have an RDD having two partitions, first partition having 3 elements, and second partition having 2 elements. So what it will do is it'll first combine the first 2 elements of first partition using the function that you have provided. Here, the function was summation, and it has called that function once. Then it'll basically take the output of the first operation and combine that result with the third element. And it'll keep on doing that again and again. So it has called your function twice so far. And at the same time, parallelly on another partition, the same thing is going on. Exactly same thing is going on. So on the another partition, we are adding up 16 and 9, and this is 25. And then these are two Spark application going on. On one application, this particular partition being summed up to a singular value, and on this Spark application on another machine, or maybe on another CPU on the same machine, this computation is happening inside another Spark application. And finally, these two values are further combined using the same function, here on the driver. So how many times have your function called here? Anybody? Four, right? 4. 1, 2, 3, 4. Now, I'm going back to the previous example. Question to all of you is, if your data had 100 elements and whatever number of partitions, let's say 10 partitions, each one having 10 elements, how many times will your function be called? How many times will your function be called? All right, let's take a look at it again. So here, how many elements are there? 1, 2, 3, 4, 5. Imagine that they were all in one partition. Will the total number of times your function is being called will be different? It'll be same, right? Because if here the extra function, let's say there were 3 partitions, so again these operations will be called, right? So generally, if you take a look at this example, if you have n elements in your RDD, the total number of times your function is going to be called is n minus 1. N minus 1, right? Correct? So your function is being called how many times? N minus 1. And hence, if you have 100 elements, it will be called 99 times. Are you clear about why it's n minus 1? Okay, so basically here, if you notice that this function, let me tell you. So if you take a look at this, every element is being processed at least once. So this sum function is going to be called once for every element, just that for initially it was called once for 2 elements. Other than that, the sum function is being called once for every element. So basically, okay, let me just draw something. Question is that, let's say we have 1, 2, 3, 4, 5. Let's say all of them are in one partition. For these ones, for these ones, for these ones, and for these ones. Correct? So this is your operator. This is another operator. This is another operator. This is another operator. So 1, 2, 3, 4. For 5 elements, it is being called as 4 times, right? Now the architecture could be a little different. Let's say they all exist in say 3 partitions, right? So this will be combined using one operator. This will be combined using one operator. This will be combined. This won't be combined. This will be basically just like that. And so this was one, this was another, and then they will all become, both be combined using one operator, and this will be combined using another operator. So 1, 2, 3, 4. All right. So in whatever way you lay out, it's going to be n minus 1 times if these were n's. Okay. So when we are so and reduce function will be called n minus 1 times. All right. Yes. Thank you, Raju. That's correct. If each partition function is called 9 times, and then there'll be 10 such values, and then out of those 10, 9 more times, and hence 99. Correct? Great. So this will be here in case of values from 1 to 100, the reduce function will call our function sum 99 times. All right, great. So this is reduce function. Now, a hard question to answer is, can we use the average? Can we use the average to do the reduce? Can we do the average using the reduce? Anybody? Can we find the average of some numbers using the reduce function? The way we computed summation using reduce, can we compute the average in the same way? Why?
It is not associative and commutative. It depends on the order. So if the order
That
changes, the answer changes. But
good, good.
the sum for some it doesn't matter. The sum is okay.
That's right. That's right. The answer, yeah, because it's not commutative and associative. We are going to talk about that now. Take a look at this problem here. Imagine that we have a sequence of numbers 3, 7, 13, 16, and 19. Why we have put 3.0 in the beginning? We are letting it infer as decimal array. All right. Now, we are defining a function called average. What does average do? X plus y divided by 2. Now, when we call that function using reduce, what happens is it'll try to compute the answer, and it would be different for all of you. Let me try to show you. Let me try to show you this. Okay. So these are basically the constructs of distributed programming. No matter which programming language do we use, no matter which framework do you use, we will be facing these kind of challenges. All right. So these are though these look like that they are very Spark specific, but they have been there for all other similar frameworks also. That's why most of the functional programming has these construct called maps and reduces long before Hadoop or Spark came into play. All right. So This is what I want to show you. So here the answer is the answer is changing every time, right? That itself is a testimony that there is something wrong with it. All right. This time it was 12.125. Earlier it was 12. Before that it was 12, right? Before that it was 8. Okay. So why? Because it is depending on in which order the elements are coming. And when we talk about Spark and distributed computing, the order in which the function is going to be executed on various elements is going to vary based on the circumstances. All right. So this time it came as 10. All right, let me give you all. Okay, try this. All right. Now, let me take you in more give you an example in more detail why this is wrong. So I just demonstrated that it gave us wrong results. It sometimes gave me 12. It gave me something else. So basically, the answer was wrong, definitely. And you will also observe that answer is wrong. Which is wrong? The correct average of this is 11.7, 11.6. Okay, 11.6, not 9, not 12, not 10, not 8, 11.6. Why is this wrong? Okay, all right. Now let's take a look at what is going on underneath. So once the average will be computed of 7.3, which will be 5. This is correct, right? Then average of 5 and 13 will be computed, which is 9. Average of 16 and 9 will be computed, right? And then average of this and this will be computed. So this you can see is definitely wrong, correct? This you can see definitely wrong because it was supposed to be 11.6, but it is 10.5. Where what exactly is the mistake here? Anybody? Which step is the mistake? If we have, let's say, this we call first operation, this is called second, this is called third, this is called fourth. At which operation the mistake is?
So for average, if you want to average three numbers, it's sum divided by three and not the sum of two numbers divided by two and then the number. So the
Right,
second step is only wrong. The first and
right,
the second step.
right. So any other answers?
Because it is not the simple average of all the numbers. It is the average of first two numbers and then the average of again the three numbers, then this like that.
That's right.
Yeah.
That's right. Correct. So the method of doing it itself is wrong, right? So reduce function does the work in this way. It can compute the summation very well, while it couldn't compute the average correctly, because here if you take a look at these three just in isolation, you see we are getting 9. We're getting 9 as output, right? While it should be 7 plus 10 plus 13, which is 23 by 3, which is different from 9. Correct? So essentially, if we have three numbers, this is not how we compute the average. The average of 3 plus 7 plus 13 by 3 cannot be equal to 3 plus 7 by 2 plus 13 and overall by 2. This is what our reduce function is doing, while the actual answer is this. So this is the mistake that we are making. All right. And you'll be amazed to know that and in a lot of problems in distributed computing, when they come as a practical problems, you'll find that you will keep wondering that why my answers are wrong. I'm doing everything perfectly right. My average function works perfectly fine. The reduce function works perfectly fine. Why is that when we are calling the reduce with average is giving wrong? So you will face these challenges more frequently in case of distributed computing, and the reason would be exactly this. All right. So question from Inda is your UDF is not defined correctly. The UDF, yes, UDF is only considering 2 elements at a time, right? Now, question to all of you is that how will I fix it? How can I fix it, right? So, all right. So again, I'm trying to demonstrate here that the same mechanism of sum was correct. Whether we sum up 3 plus 4 plus 5, or we sum up 3 and 5 and then add it with 4, or we add 4 and 3 first and then add 5, or we add 3 and 4 first and then add 5. So all of these are going to give us the correct answer, right? But the average is not the same way. So the conclusion is the reduce function that we are passing, the function that we're passing to reduce, must be commutative and associative. These are the things that we studied long back in our maths class, that what is commutative and associative. I'm going to address those again. So the reduce function must be commutative and associative. Otherwise, the result could be unpredictable and wrong. All right. Is everybody on the same page? I'm going to discuss commutative and associative after this. So the function that you're passing must have this property, or the operator that we are passing to reduce must be commutative and associative. All right. So good. Now, suggestion from Prasant is that we could just compute the sum, compute the count, divide the two. Good. Can we do sum in map, but do average in reduce step? So we can't do sum in map because map only operates on one element at a time, but summation requires more than one element at a time. Map returns the values equal to the actual RDD, while sum would return a singular value. We can do some using reduce, yes. We'll take those more examples just after this. All right. Now, what exactly is commutative? Commutative is if changing the order of inputs does not make difference to your operator or your function, then the function is commutative. If you take a look at the function is nothing but like an operator, right? So here, imagine that this is an operator. First, or this is your function. It takes two inputs, first parameter, second parameter, and it gives an output. This is the return value. These are the arguments. So whether you pass y first or x first, if the outcome is equal, howsoever, then this function is commutative. So addition is commutative. Multiplication is multiplication commutative? That's right. Now, average. Are you sure? Is average commutative? Please think about it. Take a look at the diagram. Again. So again, take a look at the diagram. The average is x plus y by 2. If it is y plus x by 2, will that be equal to x plus y by 2? All right. That's correct. So average of 3 plus 4 plus 5 is equal to 4 plus 3 plus 5, right? So therefore, the average is commutative. Now, a harder question is Euclidean distance between x and y. Imagine that we were passing x and y, x1, x2, and y1, y2 to this function, right? Right? So is Euclidean distance. Let's say we were passing two coordinate objects. This is first coordinate, and then this is second coordinate. So let's say there are points, point 1 and point 2, and we're passing those two as the argument. Each point has two values, x1 and y1, and x2 and y2. So if you're passing two coordinates and we're returning the distance, is Euclidean distance between 2 points in the space? Yes. So the distance between 2 points in the space is going to be commutative. X2 minus x1 square plus y2 minus y1 square. All right. It sounds like a little bit maths, but I believe that this much is kind of required when we do a bit of computation. And it's actually really high school kind of a maths. I mean, it's not, even if you are really afraid of maths, don't be, ask questions. And I would love to answer and would love to simplify. All right. Because most of us are not quite used to, after years of experience, we have not seen the square root as such in our daily job. So we become kind of, I mean, I myself was not very, after like 5-6 years of experience running SQL queries in a couple of jobs, I wasn't, so I've seen similar phenomena with many friends. So we kind of get disassociated with basics, and that's one of the objectives that I keep in the class, that we should, while learning practical examples, we must also learn what's going on under the hood. All right. So I would love to explain to you in details. Please feel free to let me know. All right. So yes, Euclidean distance is also commutative. Now, what is not commutative is division, subtraction, and power exponent. Right? 4 to the power 2 is not equal to 2 to the power 4. Similarly, 2 minus 3 is not equal to 3 minus 2. 2 by 3 is not equal to 3 by 2. So that is not commutative. Now, what is associative? Associative is we can add or multiply regardless of how elements are associated, meaning how elements are grouped together. How elements are grouped together. So by grouped, we mean how do we use parentheses? All right. How do we use parentheses? So okay. Now here you can see that we have here, let's say if we are adding 2 plus 7 plus 5, where do we put parentheses? Should we do 2 plus 7 first or 7 plus 5 first? Okay, in either way, when we are doing addition, we would get the same results. So previous one was, in what order are we getting the operands? Here, how we are grouping the elements, right? So that's called associative property. So question to all of you is multiplication associative? If we are doing if we are multiplying three numbers, if we multiply first two numbers and then multiply third number, will this grouping, will where we put the bracket matter? No, right? So yes. So here you can see that multiplication is an associative operator. All right. A question from Sachin is, so reduce function is not commutative. So reduce function is not something that is like an operator normally. Here, we're talking about the function that is passed to the reduce function of an RDD. All right. So the function, the operator that we are passing to the reduce function, that's what we are talking about here. All right. So, and the min function, anybody? if we are trying to find out the minimum of three elements, A, B, and C, whether we are computing the minimum of first two first and then third one, or we are computing the minimum of last two one first and then the first one, is minimum associative? Yes, please, I would request everybody to participate. It's completely okay to give wrong answer and then, you know, put your justification. So minimum is, yes, so minimum is associative because minimum of 3 and 4 and the resulting would be 3, correct? Then minimum of 3 and 30 will be 3. So whether we do it this way or we compute the minimum of 4 and 30 first, and then the result of this one will be 4, the minimum of 3 and 4 is again going to be 3. No matter how we call minimum on which group of elements out of 3, 4, and 30, we are going to get the same result, right? Similarly, the max, right. So max is also going to be the same way as minimum. It's going to be the associative, right? Now, let's take some example of non-associative functions. Division is non-associative because 2 by 3 by 4 is not equal to 2 by 3 by 4, right? Subtraction, 2 by minus 3 minus 1 is not equal to 2 minus 3 minus 1. You see, if we change the place of bracket, the answer changes, right? Exponent. So you can see 4 to the power 2 is not equal to 2 to the power 4, or we can actually put one more exponent here and you'll get the same answer. All right. Now, similarly, average. Average is non-associative. The average of 2 and 3, and the resultant would be something here. And then when we compute the average of averages, it's not going to be same. All right. So average is non-associative while average is commutative. All right. Average is commutative. Commutative is all about order, while associative is all about grouping. Or where do we put brackets? All right, so let me take a look at this average function. So average of 2 and 3, if we come, let's say we want to compute the average of 2, 3, and 4, we can't compute it in this way, that we compute the average of 2 and 3 first, then the average of the remaining. All right, so this way the answer for the average of 2 and 3 will be 2.5, correct? So the average of 2.5 and 4 is going to be 3.125, right? Here, while the average of 2 and 3, so this is actually the same thing. Let me just, yeah, thank you for asking this. Let me say 2 and 4 and 3 here. Okay, so this time we are computing average of 2 and 4 first. The answer, the average of 2 and 3 would be 3, right? And then we have this. All right, great. Thank you, David, for noting that. Okay. So average is commutative while the average is not associative. Okay. A point from Abhida is the first average is associative, second is not. Okay, which first and second we are talking, Binta? So average is commutative, but average is not associative. In the previous slide, we talked about as average being commutative. All right. Correct. If we take an average once, then that is correct. So, but we can't when we take when we talk about associative property, here we are talking about operating on two elements in a single shot, right? So that if we operate on two elements, then the answer is going to be wrong in case of average, and therefore average is not associative. Yes. All right. Great. Now, let's try to solve some of the problems with Spark using whatever knowledge we have gained so far. Any questions at this point? Now, just now we saw that we cannot compute the average using the standard way. And most of you suggested that first compute the sum, then compute the count, and divide the two numbers. All right? Then divide the two numbers. And that's what we are doing here. So you see, here we are first calling this reduce, then we are calling count, and then we are dividing by the two. So my question to all of you is, what is wrong with this approach? Will this give correct answer? Okay. Question to all of you is, will this give correct answer? Okay. Okay. Yes. The point from Prasant and Binda is that it could be, it is not the best one. Prasant says that it is slow. Good. Why would it be slow? Anybody? A question from Hitendra is, it will be by partition. Yes. So basically, reduce will compute the summation the way we described earlier. You'll get a single number. Similarly, count will do the way we talked about earlier, that it will basically count partition wise, and then you'll get the results. That's right. So these are, so this is an action and this is an action. And we are calling actions twice. Every time you call an action, the entire execution is going to happen. Then we will wait here till the first this reduce finishes. Once reduce finishes, then the counting will start, right? That is the main problem. So if this is taking 2 seconds, this will also take, say, 2 seconds closely, and then the overall time will be 4 seconds. All right. So we are computing RDD twice. We are going to use the console as opposed to the notebook for this. Why? Because the notebook does not show us the diagnostics, and we want to take a look at the diagnostics. All right. Now, question to all of you is, can we compute sum and a count both together? Can we compute sum and count in a single pass? Can we, as we are going through the elements, can we just do the counting and summation in the single shot? Anybody? I'm sure most of you are seeing the PPT. And okay, all right. Now here, so imagine that we have two elements, and both the elements we convert it into total and count. So we can combine these two elements by summing up total as well as summing up the counts. All right. So if we convert our element, each of our element into a pair, whereby first number in that tuple represents the total value and second number represents how many numbers are there in this total, the counts. And then we can actually sum up these two parallelly, right? We can combine these two tuples in this way. And this operation is going to be associative and commutative, right? Whether this is first element, this is second element, it'll always give you the right answer. So if our RDD has 4, 5, and 6 in the value, we will first convert it into a tuple. Okay, let me explain again. So if we parallelly compute the total and count, then we will be able to get the outcome. Let's take a practical example. Let's say we have an RDD having three numbers, 4, 5, and 6. Now, the first thing we will do is we will convert this RDD into a tuple. First value representing the total, which is 4. And how many are these values? 1, right? So this is the total is 4 and the value is 1. Similarly, 5, 1, 6, 1. And then we will sum up two tuples, this tuple and this tuple. So 4 plus 5, 1 plus 1. So counts and sums both are being counted together. Both are being counted together, right? So, and similarly, we are combining this and this in the same fashion. So it's a single RDD. It's a single RDD. Here, this is another RDD being generated by converting it into a tuple. And then we are getting the results. All right. So question from Sachin is, will there be three RDDs? So do you mean that there will be one RDD representing the input, other RDD representing this one, and third one as the output? Is that what you mean? Okay. So yes, in that way, there would be this kind of computation, but don't worry about it. It is going to be really, really efficient. All right. So RDD is, though it looks like it's a data store, but it's just a representation of steps. Okay. So here you see that in the final one, once this we got this value in the driver, the outcome of this will be a pair, right? The outcome of the reduce here is going to be a tuple in which the first value is the total and second value is the count, right? And the outcome is 15 by outcome we can compute locally. Once we get this tuple locally, we can compute this locally. All right. So this is what we are doing. So let's say we are parallelizing this and in three places, and then we are converting this into a tuple. And then we are defining our sum and count function in this way that it takes is taking two tuples, tuple 1 and tuple 2. X is tuple 1, Y is tuple 2. So we are summing up the first element of both the tuples and second element of both the tuples and returning a new tuple. All right. So we are summing up totals and we are summing up the counts.
Sandeep,
Yes.
RDD is a representation of data. So we can say that, I mean, if we have three RDD, then will it not take more time?
Actually, that's the interesting part. So these RDDs get reorganized. So this RDD underscore count that you see, right? It looks like that it's a new, it'll basically first compute the map and then do this. Actually, it's just a step. Uh,
Yeah.
yeah, it's just a step in the job execution. This one right now doesn't hold anything actually. It just hold the this information that this will be computed using this. When we do reduce, then this processing is going to happen. It's not. It's basically a processing step, and you will get the idea as we go ahead because the RDD is kind of most misunderstood in the words, but as we do more practical examples, you will be able to understand that okay, this RDD essentially is a um, step, not really a data. If we have, let's say, 5 maps, right? RDD underscore count, we do filter and all of that. So when we do execution, all of those steps will be combined into single value, and you will not have any overhead as such. All right. So so the overhead is not too much in case of new creating new RDD. The overhead is in executing in doing the as in doing the operation, the whole action. That's where the overhead is. Second, the overhead would be when we do the shuffling steps like sorting the data or grouping the data. There, since the data will be moved from one place to another, there will be the overhead.
Okay, I got it.
All right, great, great. So yeah, that's the idea that it takes some time to sink in. It took some time for me also to sink in. So it's an important question to ask. A question from Raju is that the intermediate outputs will not be formed into RDD in the process. They, yes, that's kind of an internal to job execution, and will it'll take care of that. All right. So now coming back to the problem that, so I hope this is clear to everyone. So the way we are computing average is by totaling the totals and by totaling the counts, right? By adding or summing up the counts as well as totals, both the things in a single pass, so that we don't have to execute two jobs separately. Okay, let me go through this. What is it that we're trying to do? All right, let me try to execute it. So here we go. All right, so this is our RDD. Okay, so you can see that this is the RDD that we have defined. All right. Now, next part is we are converting this RDD into each element into tuple. And when we want to operate on every element, what we do is we use the map function. And here, this function that we are anonymous function that we are passing, what it is doing is for every element, it is creating a tuple by putting the second value as 1. All right. So now the RDD count that you see, I'll just say collect. Okay. So you can see this is an RDD where every element is a tuple, where every element is a tuple. Why did we do that? So that we can do a reduce, so that we can sum the total and counts together. This is what we want to achieve. This is what we want to achieve. So if all we want to do is convert every element into the tuple and then merge these. Okay, since we can't really merge 4 and 5, the way we want to merge it is the way we want to reduce our values is that we want to co- compute the total as well as the counts in a single reduce. We want to create a function that could do both the things in a single sort, right? So imagine that, let's say you have Okay, imagine that you have, say, okay, imagine that you have, say, 3 rooms full of coins. Okay, so imagine that you have 3 rooms full of coin. Okay, and you send 3 persons to these 3 rooms and ask them to compute the average denomination. If these 3 people return to you with average denomination in every room, you have coins in every room. Okay, each room has some coin. Let's say this is a really rich temple, and temple has many coins and many a lot of money packed in the in the various rooms far away. And you send 3 priests to, or three what do you say, 3 persons to count the average denomination. If they give you average, you can't really compute the average of averages, right? Therefore you ask them that, hey, don't come back with the average, but come back with total value and the count. Okay, give me, come back with 2 numbers instead of single number. Okay, so they will all come back with saying, okay, we have 1 million, uh, 1 million in this, and we have around 5,000 coins or 5,000 notes. Okay, similarly, they all will do that. So basically, if we got, say, so if they went and brought these 3 numbers, so x1 and c1, x2 and c2, right, and x3 and c3, then we can sum up these x1, x2, x3 again here, and then counts we can sum up separately, and then whatever is our x, the outcome, we can basically compute the average denomination by dividing x with c.
But Sandeep,
Yes.
yeah, I have one question. So here, actually, even if they come up with the average, from each of the
Mhm.
boxes,
Yes.
then also we can compute the final average, right? We just
No,
divide it by 3.
no.
Why not?
Imagine this, that that's what we just discussed. So
Yeah.
if, let's say, there was 1, 2, there
Okay.
was 3, and there was only let's say only one coin called with 3 denomination,
Okay.
and there
Right.
was one coin here in this room with 5
Right.
denomination, right?
Right.
The average of this one will be 1.5. The average of this will be
3.
3. The
Okay.
average of this will
5.
be 5, right? The average of these 3 numbers will be
9.5 divided by 3,
9.5 divided by 3.
which is
Ideally,
3.15.
ideally, how much it would be? 1 plus 2 plus 2.
3.17 roughly, yeah.
Yeah. So
3.17.
yes. So in reality, it is going to be 11.4, right?
Yeah.
So which is these 2 numbers are different, right?
What? Oh, no, no, no. 9. Okay. Oh, okay, okay. Okay.
So actually, this is correct. This is wrong.
Okay. So you're saying
All
it's
right.
8, and then so how did it become 11? Sorry, like 1 second.
So
So this is
1
5.
plus 2 plus 3 plus 5.
Okay, okay. So okay, count. Okay, okay, got you. No,
All right.
no. So okay. So this 1, comma 2, denotes
2 coins.
the total, right? Okay, okay. 2 coins. Okay,
Yeah.
okay, got you. Okay. I thought
All right.
it's one of two actually, but it's 2
Okay.
plus. Okay, okay.
Okay, okay, yeah. So basically, that's exactly the problem. So what we do is, instead of asking these priests that, hey, can you bring the average? We then don't tell them that we want average. We tell them that just count the, just give me the summation and give me the counts. Okay,
Mhm.
and then we do the average of we do the summation and counts, and in the final number, on the final number, we do the division. All right. So we distribute the work of summation and counting, but we do not distribute the work of average. Why? Because average is not distributable because it's not commutative and associative. It's not essentially associative, though it is commutative. So therefore, we compute the totals and counts parallelly and then do the reduce. All right. So I hope this is clear to everyone. Should we move ahead?
Yeah. Yeah.
Wonderful. Wonderful set of questions. So all right. All right. A question from David is, so this is mean average, correct? Yes. Question is, how is the median calculated? Right? So now that's a very hard question to answer. And if anybody in the class can answer that, it will be wonderful. All right. But I'll park that question aside. Maybe we can take it up separately. So can the median be distributed and computed? All right. All right. So since the median requires the data to be sorted, so it'll require a lot of steps than the usual ones.
Sandeep, I was
Mhm.
wondering if can you do sorting in parallel?
Yes, we can do sorting in parallel.
Yeah, then if you can do that, then you can get the median. Because once you
That's right.
have the sorted values,
That's
then you can just get the mid value.
that's right.
So
That's right.
what's the underlying architecture for sort? Is it merge
Yeah.
sort or quick sort? Which sort is it?
Okay. Okay. So a very good question, and I think it's good that you asked that question, and I think let me answer Binta's question once. Then I'll come back to the sorting. So a question
Okay,
from
thanks.
Binta is: are there map reduce functions in Python to do similar tasks as there in Scala? Yes, that's right. Actually, the Python was the one, but not Python. The Perl was the one to come up with map and reduce long back in 2003 when we were doing grid computing. We were using the Python's maps and reduces long back. All right. So around like say 14, 15 years ago. Now, the same thing has been there in Python and the same thing is there in Scala, and the other languages have also adopted it. Now, are these functions with pandas? Yes, pandas has also provided a function called map on top of data frame. All right. So that's a question. Now, let me just give you a very high level architecture of sorting. So okay, so if you want, I can okay.
I would just add to this. Actually, I had read an
Mhm,
article somewhere, and there's some competition where you have to do
mhm.
some sorting, and
Right,
the
right,
person who
right.
does the sorting the fastest wins the competition.
Correct, correct.
So
That
Databricks won it one time, I think last year
right,
or something.
right. That's what I was coming to. So it's called sorting benchmark, and so I'm just contemplating, should I walk you through my map reduce session that we generally have because we have discussed it there. That's what I was contemplating. So sorting is a very important phenomena, and sorting is kind of the heart of. Let me just walk you through the talk. Okay, let me just walk you through my discussion on the same topic. All right. So okay, I think I'll just walk you quickly through the the sorting. Okay, so in this we talk about sorting. Okay, so Spark also provides something called sorting. We are going to talk about how to do sorting with Spark in future, but for now I just want to give you a quick overview of what does it mean by sorting. Right, sorting is let me just skip this part. All right, so sorting is a very, very important phenomena, that there is something called sorting benchmarks. Sortingbenchmark.org is a website where most of the big Bs, most of the people compete on sorting. And once the team who built Spark, they won the competition. Before, the first one to win that competition was Google in 2011, and there they were able to sort 10 petabyte in 6.5 hours using 8,000 computers. They used the MapReduce framework because they were the one to come up with the massively parallel framework called MapReduce to do the sorting using many computers. So a question from David is, what slide deck you're on? It's a separate slide deck. I don't think you will require this one. So we'll just walk you through these 5 slides here, and then we'll go back. Okay. So now there is a sorting benchmark, and then many people compete there. First, Google won it, then Hadoop won it in one of the years, and then MapReduce, the Spark won it, and that's why Spark actually overtook the job of Hadoop's MapReduce. All right, so sorting is the heart of most of the computer problems. So I'll talk about this. So every SQL query is impacted by sorting. So whether it's where clause, if in the where clause in the in a table, when we are retrieving data, if we have indexes on the table, the data is going to be extremely fast. The retrieval is going to be extremely fast because we're going to just do a quick search uh, onto the index, and we are going to get the result. If we have, if the data, if your query is involving the group by, then it involves sorting, because group by, the way it works is we sort the data, we go from top to bottom, and if the keys the value the numbers are same, then we group them together, and so on. So grouping is actually done by sorting. Then joins. When you're joining two tables, if the both the tables are sorted by the same key on which we are joining, then it is enhanced by sorting. Then distinct. Distinct, of course, is sorting, because the way we compute distinct is we sort the data, go from above. If the consecutive values or the values which are next to each other are same, then we remove one of those. So an order by is, of course, sorting. So almost every computation that we do, whether we are like the way we are talking right now, here a lot of sorting is going on under the hood. All right, whether we are using, so almost every algorithm uses sorting without even we thinking about it. And so most of the algorithms under the hood depend upon sorting. A question from Binta is average function a building function in Scala? If so, why not use it directly? All right, even if we use that, still the answers will be wrong. All right, okay. For the same reason, it's not because average function is wrong, but because the way is being called by Spark was wrong. All right, let's come back to the point now. So here I want to write. So here I have tried to describe what happens. So So the same thing I can actually describe to you that, right? So imagine that we have three partitions, 1, 2, and 3. And Spark, we ask that, hey, can you sort my data, right? So what it is going to do is it's first going to sort these records partition by partition, these records, okay? And then it's going to shuffle them, okay? It's going to shuffle them, or we call that merge sort, okay? So the way it works is that so I'm just going to explain to you this. So imagine that we had, say, 10, 5, and we had 6, and say 9 and 1, okay? And then we had 2 and 15, right? So first of all, the sorting, the way Spark is going to do is, it is going to first of all sort these records partition wise, okay? So it is going to first sort all of them per partition, okay? So this will become what? This will become
5, 10.
5, 10, right? 5, 10, correct? Then it's going to do the same thing for this also, okay? So this will become 1, 6, 9, right? It will use any of the sort, the standard one that we do, either merge sort or quick sort is going to use either of the techniques there. And once we do that, let me just do it, and let's see if I can move it. All right, so this is already sorted. It will not touch any, it will basically do the sorting again. Please keep in mind that whenever we are sorting, we don't, detecting that the data is sorted also takes equal amount of time as the sorting. Okay, so we generally don't really detect whether the data is already sorted. Instead, we just sort the data. And some of the algorithms actually work worse if the data is already sorted. Okay, so some of the algorithm, if you are trying to sort the sorted data, they will actually become really slow as compared to humans. When they see the sorted data, they don't sort it again. But algorithms, some of them are heavily impacted badly. So say if you are using the binary search tree in order to sort the data, then it's going to make it slower. All right, next is that once we have sorted it, then what it is going to do is it's going to kind of merge them. It's going to kind of merge them and create new set of partitions here. All right, so it's going to kind of merge them. So this will when it's going to merge, what it is going to do, it's going to compare the first element of all of these, right? Since this data is sorted, so it can compare the head of from all of the queues and then put it in the output. So I can just show you this UI where yeah. So imagine that we have these queues, like two queues, and they are, both of them are sorted. This is coming from sorting one partition. This is coming from sorting another partition. So we can easily merge them. How? We can just compare the head of every queue and pick the one which is smaller or shorter. All right, and then we remove the one which has been picked, and then we compare the head again and repeat the process. Okay, we compare the head again and repeat the process. So we can do the same again and again, and we can keep on doing it again and again, and we'll finally get the sorted queue. All right, so I think you got how to merge the sorted queues. So this
A
is
question on this. The
what?
merge, a quick question. Merging
Mhm.
is also parallel, or merging is only two partitions at a time?
Merging is generally sequential, two
I think
partitions at
just
a time.
two, right? Because it again creates a confusion if it's more than two.
Right, right. So There are some more techniques to merging. If you have only two queues, it's easier to merge it the way I just described. But if you have more than two queues, if you have like three queues or five queues, imagine that you have 6 queues. Now merging 6 queues is actually hard. It's going to take more time. So there is a data structure called min-heap. So we create something called a min-heap out of the heads of every queue. We pick up, these are 6 queues, first, second, third, fourth, five, six. So each queue is having 3 members. So what we do in these cases is, if we see when we have to, it's a standard interview question. And this is the interview question probably Amazon would ask any data engineer in their second round. What is the second round at Amazon? At Amazon, the first round is generally the normal algorithms and general discussion. If you're going for, let's say, kind of a company called Amazon, then they'll have a second round with a really senior person. That's called a bar raiser round. And in the bar raiser round, what happens is they ask you a design problem. And generally, most of the questions that are asked to the data engineers are related to distributed computing. Okay, so one of the questions that is generally asked is how do you merge, say, 15 or say 100 or say 1,000 sorted arrays into one. Okay, specifically if they are coming from multiple machines. So the way the answer is that we create a min heap. This is a min heap. What is a min heap? Min heap is a data structure. We call them priority queues in Java. We have similar structures in Python, similar structures in other languages. The quality of this data structure is that it always gives us the minimum value really fast. So we can insert values into it, and the minimum value always floats to the top, and you can always extract the minimum value at really fast speed. So all we have to do is create a min heap. This is all we have to do is instantiate min heap and insert the head of all the queues into this min heap, and then pick up the shortest value from the min heap, and then figure out from which queue did this min heap come, this value come from. Then if, let's say, this is 1, we are going to pick the second value from here, and so on. So we're going to here, this basically this data structure is doing the comparison here, like the comparison, the way we are
Mhm.
comparing ourselves. This comparison is being done amongst multiple values by the min heap. Yeah, go ahead.
I didn't understand the min heap concept. I understand
Okay.
the data structure, but like how
Mhm.
many min heaps are formed? Like just
What?
one per column or one
Okay,
per?
good. Good that you're asking that question. So here, what we are doing is we are creating a min heap. How many elements are
Yes,
going to be there? The number of partitions we have in our RDD. So how many queues are there? One queue,
6.
2, 3, 4, 5, and 6. So 6 elements are going to be in this min heap. So
Okay.
we will take the head of the we'll take
All right.
the head of all of the queues, all the
Mhm.
people who are, imagine that you are standing in an assembly, a prayer assembly, and there are 6 queues and you have to merge those 6 queues. What you're going to do is pick up the people who are standing in the front, put them in the min heap, and the min heap will give you the smallest element out of those. You extract the smallest one, put them in the output, and figure out this smallest element came from which queue. You take
Okay.
the second element from exactly same queue from which the smallest came.
Okay.
Okay.
So the minimum can be obtained in big of one, right? Because the first element is the minimum.
Yes.
And then your second, again, when you pick up the minimum, you have to insert that element into the minimum into the min heap or just extract it from where you picked it up.
Yeah. So basically what, no, you basically insert it and again the smallest will float up.
Okay, you call min heapify again on the heap.
Yes, yes. The moment we insert any element again, the smallest element will float up
To
automatically.
the head. All right,
Yes.
got it.
Okay.
Okay, thank you so much.
All right. So this is how this is a standard question that is if you are going for, let's say, data engineer or a senior engineer position, this kind of questions might be asked. All right. So
So
although
Sandeep, how it is
yes,
forming the tree structure? Eh,
this one.
yes.
Okay. So basically, this is basically a standard concept called min-heap. Okay. And it's a data structure which there'll be an animation. I wanted to show you the animation. Okay. So, all right, is there animation for this? There was a good animation. I think you could take a look at that animation and min-heap animation. Okay. And yeah. So what this is a very interesting data structure that the okay. So what happened here? It did not work, or it's not going. Yeah. So automatically the things keep on floating up as we are inserting values, and then it is the top one is going to be automatically become the smallest. So that this is what's going on internally. Okay. So you can just go through the min heap at your time. Just remember that the quality of this algorithm, this min heap, is that when you insert an element to it, automatically the smallest will float to the top. Okay.
So the insertion always happens to the leaf, right? And
Yeah.
yeah, so
Yeah.
and then it automatically floats up based on the comparison internally.
Yes. 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 It is going to compare this again, this again, and it'll going to go up. So imagine that here you're inserting a new element, it'll be compared to the head, then again and again, it'll keep on going up. So that's how it happens. And
So complexity would be log n
a kind of yes,
because only one part of the tree would traverse.
yes, yes. All right, good. So we
Sandeep,
can,
what are the main data structures asked in the interview?
so yeah. So in the basically you should know about what is a hash map. You should know about say what does it mean by a normal tree. So just go through any basics of data structures. But most of the data engineers, you will not be asked too much about algorithms and data structures. You'll be only asked about like the things that we have talked so far. That a general question is that given X numbers, how would you order them? How would you solve that kind of a problem using any of the frameworks? So those are the kind of questions will be asked. And okay, it's a good question. So I think I would, what data structures are asked in data engineers interview? So tell you this some important thing. So if you are going for companies like product companies like Amazon or Google or similar companies, they would ask you the data structures more. While if you are going for a little senior position and specifically in the application side of the data engineering, then they are going to ask more about application part, as in they'll ask more about Spark, how do you do importing of data, how would you do loading of data, and so on. They will ask less about algorithms and data structures. All right. So that's one thing. But anyway, I'll try to structure my thoughts on interviews of data engineers, and let me try to put down the thoughts more clearly than answering now. Okay, so I've taken a note of this. Probably
Sandeep,
I'll be
also tell us
writing
about
a
any
blog
website which is
post.
like similar to Geeks for Geeks
Okay,
for data
okay,
engineers. But
all right, all right.
all right, thank you.
Oh, I kind of missed the pic. All right, thank you, Sachin and David. Okay, so I kind of got involved. So the idea was to talk about a bit of min-heap, and min-heap, even if you don't understand it, this part, if you understand, this is good enough. And this is basically what we are talking about, merging the sorted data, merging the sorted data. That's all. All right. After that, we'll continue our discussion, and let's take a break for 10 minutes. Learned about the approaches to compute the average, and we came up with the approach where we operated on tuples, and we basically did the counting as well as summation together and then divided by total by the counts, right? In a single shot, in a single you can say single pass. Okay, so this is what we did. I hope everybody is okay with that. And all right, a question from Hitendra is, can you explain the third line in the approach? You mean this one? Okay. All right, this one. Okay, let me just try this one. Okay, so there are some more things here. Let me try if I can break it down into simple parts. Okay, if I can break it down into simple parts. So this function that you see here this is actually equivalent of you see this function that this one is to tuple, right? We are creating a function called toTuple, which takes one argument and returns we call it tuple 2x comma 1, right? Something like this. And then we are calling this function, we are calling this function this way. Okay, so this is what is this one line is equivalent of these three lines. Okay, I'm sorry, I'm actually getting into Python mode again. Okay, so yeah, so this line is equivalent of these 4 lines. Now let's talk about the second one. Let me break it down into the next one here. All right, so what's going on here is let me just convert this into like multiple steps. So we are defining a function called compute sum and counts, or we can say total. Okay, and it takes two tuples, tuple 1 and tuple 2. Okay, and it returns another tuple. Okay, and all it does is it first computes the what do you call sum equals to t1 dot underscore 1. This means first value of the tuple, right? Okay, so we are saying t1 dot underscore 1 plus t2 dot underscore 1, right? Then we are doing the counts. The counts is t1 dot underscore 2 plus t2 dot underscore 2. All right, and then we are returning a tuple with sum comma count. That's what is going on here. So all right, this one is second values, right? And what is the first value from each tuple? First value is this, the actual value. Second value is 1 initially, and then the second value, the counts will start adding up, and then it'll become, right? Second value is initially 1, the counts are initially 1 for every value, like as you see in this diagram, the counts are initially 1 for all the values. Sum, this is going to be like this. So that's what we are doing. All right, Hitendra? Was I able to explain? Okay. So great. Actually, the thing is that long back people were just using a standard example of word count in the Spark. And I wrote a blog on why the computation of average is inefficient in most of the implementations. And then this interview question actually picked up. And these days, people, when you go for data engineering question, they actually ask these questions. Okay, so the interview question that is there on our blog is kind of de facto for many interviews. All right, so that's I wrote long back this interview questions on Spark and others that kind of became popular, and many people have copied and pasted and read it in the same thing, and it's being used on a large scale. So when we were called no big data, we were basically then at that point of time I wrote it. Okay, so this is just a dummy code. There would be errors in this. I have not debugged the errors. Okay, so here these two approaches are identical, and these two approaches, this and this, are identical. All right, so
Sandeep, how the count will be T1 plus T2? Count will be the total number of n numbers of.
okay. Question is, let's say here, take a look at it here. Count is initially 1 for all, right?
Yeah.
So so you can think of if we sum up 1 from using the same reduce mechanism, at the end of it, we are going to get the total, right?
Okay. Okay.
All right. Imagine that these were RDD was full of only ones, correct? At the end of the day, if you sum up all of that, you'll get total counts, right?
Correct.
All right. Wonderful. So I'm just wondering, can I make it a little bit shorter? If we have, say, here, if we have, say, 1, 2 plus 3, 4, what will be the answer? Oh, we can't add. No, we can't add 2 triples, just like that. No, it doesn't add. Okay, so if this added correctly, then we did not need to write such a function. All right, great. So the approach, if you try to run these two approaches, right? All right, thank you, Binta. So actually both Scala and Python, the approach is actually identical. So, all right. So if you are learning in Scala, you will be able to naturally solve the problem with the Python also. All right. So you can actually just, if you are good with, okay with Python, you can just write PySpark and actually write your code exactly in the same way and get it executed. Okay. Just a very tiny tweaks. Everything will remain identical. All right. So if you take a look at the time it takes to run these, if you actually run the program, I think we did not run the programs. Okay, let me just try to run the program end to end and then show you how much time did it take. Okay, so in the end, you see this, it took this much time. Okay, it took this much time. It took this much time. All right. This much time, right? Now, if we do go back and try the first approach, this approach, right? And take a look at how much time it's going to take, right? So So it says that it has taken this much time to compute the second job. Okay. And the first job took how much time? Okay. So basically there are two jobs here that are running. Okay. And right. Let me go up. Right. Here you see there are basically two jobs, and okay. So this number that you see for execution of these jobs, this number is, since individual job is really tiny, it's essentially is going to vary a lot. Okay, if we run the same thing, it might come up like 0.01 second. The important part is there are two jobs, and both of them are going to take similar amount of time. If let's say go back and we run it a couple of times, this one is going to be extremely fast. Okay, and we can just run it till here and then see the outcome. Let me just try to run it again. And now this time it took only this much time. And if I just run it again here, so you can see it took this much time. So a single job is kind of taking this much time, while the two jobs individually are taking the time taken to individual this job. So you can see that the second approach is twice faster than the first approach. The second approach is twice as fast as the second approach. No, sorry, second approach is twice faster than the first approach. Why? Because first one has two jobs and second one has only one job.
Sandeep, quick question. Why are
Yeah,
the runs taking different times?
runs
Like the
taking
four,
different. Yeah, yeah, runs taking
because
different time because there is an overhead. Because here the actual work is very tiny. Actual work is very tiny. Therefore, you are being impacted by systemic changes. If there are the CPU is busy in other things, that is impacting more than actual work.
okay, so actually the concept should be if you rerun the same code, it should take exactly the same time, right? Because
Yeah,
we are not
provide.
using the cache or something like that over here.
Correct,
More or
correct,
less, it should be around the same time. But here we see
correct,
like a significant difference between the two times
correct, correct.
without
So
any change.
this, yeah, this timing that when you run it again and again, you will see that this time kind of varies randomly. Okay, why? Why? Because your actual work is almost taking 0 seconds.
Okay.
All right. And most of the overhead is in the execution of the job, going and
You mean
coming
the
back
scheduling?
from multiple CPU. Yeah,
Like you mean that it's waiting
scheduling
in the
is
queue
one of
for
the
some.
reasons. Correct,
All right.
correct.
Okay. Thank you. Thank you.
So those semantics, the systemic changes are impacting more because our actual work is really tiny. If we are dealing with some amount of bigger data, like a couple of GBs or say 20 GB or 30 GB, you will be able to see this change. So they see this difference very clearly in the two approaches. Okay. So a question from Saris is, I mean, the difference is about 50% only, right? Not 2x. Actually, the difference is here you see that the approach one was taking 89 milliseconds and second one is taking 58. And in reality, if you run it multiple times, like 15, 20 times, and then you average it out, the various runs, you'll find that the average time is almost like 2x. Okay. Average time is like 2x, and because summing up tuples is not too different, that overhead is very tiny as compared to running the job. All right, so you can say that it'll be kind of maybe if not 2x, it'll be 1.8x kind of difference. So yes, so you can see the difference in the two approaches. And You will notice that in practicality, in one of our student who actually joined the course, he was uh, he was basically doing this collect and running like 10 jobs every time. And what we did was we basically then I asked him that why don't you just go through at least the first session, the current session, the one which we are going right now, and then solve your problem again. So he was actually able to bring down the time around 2000 times. Okay, 2000 times. And that is the difference that plays when you have the distributed computing, because suddenly the moment you start bringing the data to one machine, suddenly the entire time goes in that instead of computing. Okay, so you will notice that just by being mindful of where, if you are mindful of like where is my data, then everything will be okay. It's about being mindful of where is the data and how many jobs are running and what's going on beneath the skin. And this is the reason why I'm going through this session in detail, because this one pays back in a bigger way, even though a lot of people would like to jump directly to say started using data frame, started using Spark streaming, and so on. And when I look at their code, when I look at their approaches, the approaches are really inefficient. And when the data is bigger, trust me, the time that it takes for most of the people is around like 1,000 times than the actual one, or maybe 10,000 times sometimes. So it's very important that we go through this approach step by step, and we all of us should participate. All right. So good. So we did one interesting part, that was computing the average. Now let's move a tiny bit. How many of you remember what was standard deviation?
As far as I know, how far you are away from the mean, right?
That's correct. That's correct. All right. So yes. So the standard deviation is a measure of how spread out your numbers are. If All right. So if your numbers, so here, let's say what is this? This is a histogram. Histogram is nothing but on x-axis you have the numbers, on y-axis you have the population, right? Like in a class, how many people are near the mid value, how many people are scored 100 value, how many people scored 90 marks, how many people scored 70 marks, and so on. So this is that graph. So the histogram is an important graph. If you are going for, say, machine learning or something, then, right? So, okay. Point from David is that 89 would be benchmark, thus 59 is 230. Yeah, kind of, yes, you are right. If we are considering that to be a benchmark. And yes, so I would say that these numbers are a little misleading because they are basically they represent how much time it's taking for execution of the job, while our actual task is kind of zero. Okay, so the important point is to understand in these cases is that the actual job is going to be 2x from the original. Okay, so again, the approach 2 is going to be twice faster than the approach 1, or almost like twice faster. That's what I want to say. Yeah. Somebody wants to say something? It's unmuted. Okay. All right. So yes, great. Let's move on to the standard deviation. Now, so standard deviation, I was trying to describe to you the standard deviation. Standard deviation in this case is going to be smaller, while the standard deviation in this case is going to be bigger. The standard deviation in this case is 50 because the data is spread out. The data is spread out. That's this one. And here the data is very narrow. Almost everybody is doing very great in this class. Like people are getting marks between 72 to 130. Okay, so therefore it doesn't have too much of deviation in the class. While this class is very much varying, people are getting 230 marks, people are getting 100 marks, and people are getting all like full range of marks. Okay, from 0, and even negative marking is there. So you can see if these are the two classes, this one and this one, here everybody is getting really good marks and near to the average. Here the people are getting huge variance. Now, so the standard deviation in this case is going to be small, while the standard deviation in this case is going to be high. Okay, so standard deviation is a measure of how spread out your marks are, your numbers are. All right, the way we compute it is using this kind of formula. It's a square root, it's a square root of the average of the summation of the squares of the values subtracted from the mean. So the way you do is you first of all find out the mean. Mu here is mean, xi means each number, sigma means summation of all the values from 1 to n. So for every number in xi, we have, let's say, 50 numbers. So what we are going to do is from each of those 50 numbers, we are subtracting the average, and then we are squaring that, and then we are summing up the squares and dividing by n, which is the total values, and then we are doing the square root. This is called standard deviation, and standard deviation is something, let's say, data scientist comes to you that, hey, I want to do standard deviation on the big data. We have a few billion numbers, and we would like to do the standard deviation. And here is my program that does the standard deviation. Okay, so one way that we generally will try is that, okay, let me just run it. Let me just run the standard deviation on a humongous data. Let's say our data is in a file, and we want to compute the standard deviation. So what we'll do is we'll bring the data to local machine, local node, and we'll try to do it in memory. And that's where the problem would arise. That's where the problem would arise. So now you will think about it and talk to the data scientist that, hey, looks like your formula, we need to understand your formula, what is it doing, so that we can make it distributed. So the life is, as in the way we always looked at things was that, okay, the whatever we considered these all these formulas as a black box, and we thought that we should be able to execute them just like that on distributed computing, but that's not possible. We will have to rewrite many functions. We'll have to revisit the algorithms in order to make them distributed. The entire approach need to be revisited and readdressed. You need to understand the actual approach and then see how you can make it distributed. All right, that's an important part, and this happens very often with us. A lot of people with their PhD thesis, they come up with their algorithms and say that, hey, can we make it distributed? And then we look at the algorithm, we sit with them, we analyze each step of their algorithm, and then say that, okay, this needs to be restructured, and we need to make this in parallel, and we need to do this in sequence later on. And can we convert this logic, instead of going through sequential, can we make it like parallel? All right, so like for example, word counting generally people do in memory and doing the hash map, but that same thing could be done using sorting, and sorting can be done parallelly. So many approaches need to be, as a data engineer, one needs to sit down with the data scientist, look at their algorithm and analyze it, that what part can be parallelized. All right, so now in this, the thing is, can we compute this square root of a single number? This is a single number, yes. Can we compute divide by n on a single number? Yes. Now here the summation we can compute definitely. This is a summation of all the numbers. We can definitely compute the summation. Can we compute the, can we subtract each number by mean? Yes. Can we square that with, can we square it individually using Spark? Yes, we can do that. All right. So we have done the computation of, um, we have done the computation of mean. We can subtract that mean from each number, square each number, and then using the reduce, we can sum it up and so on. So we work out the mean. Then for each number, we subtract the mean and square the result. And then we work out the mean of those squared differences. Whatever we have done in first step, we'll compute the mean of that, meaning we'll sum it up and divide by the counts. All right. So, and take the square root of that and we are done. Okay, so this part, since this part involves only one value dividing by n and square rooting, this can be done locally. All right, while this one should be done using multiple machines if your numbers are, say, billions. Okay, so let us calculate the standard deviation 2356. So first of all, we'll compute the mean. The mean of this is 2356. So we sum up and divide by 4. Then we subtract each number by 4. So we get this, and then we square it, then we get this, and then we sum it up, then we get this value. And afterwards, we are going, we are dividing by n and summing up. We are dividing the sum, which is 10, by 4, and then doing the square root. So we're getting the standard deviation as 1.5811. All right, is this approach clear to everybody? What's going on in the standard deviation? All right, so it's a classical example, and this would happen quite often when you join a company which is focused on data sciences, that they come up with their strategy and approaches and then say that, okay, let's plug in the distributedness into it. The distributedness cannot be plugged in at later point of time if you are writing your own algorithm. The algorithm, the people who are designing algorithm need to think in the distributed fashion. Okay. So let's take a look at how will we write the same mechanism using Spark. First of all, let's just create a example RDD. Then here, first of all, we are mapping it. We are just mapping it. Okay. So here, what is that we're trying to do? We are trying to compute the mean the way we did earlier. Once we have computed the mean at this stage, then we are computing the we are subtracting the values. Then we are subtracting the values and squaring it. So what we did was we did map underscore minus average. That's equivalent to saying that map, and we are executing a function which takes an argument underscore and then subtracting the average from it. Then we are writing another map which is squaring the values. So we can chain the map this way. And then we are summing up the values of the previous step. Afterwards, we are doing the square root after dividing by count. All right. So this is our strategy to compute the standard deviation. Okay. All right. So the core objective of this exercise is that we need to understand that most of the algorithms, even as simple as the average, we might have to readdress because of distributed computing. All right. Okay. So sum of square differences is 10, and then we basically import the math all the functions from math. Math dot underscore, this is something that we did not discuss earlier. Math dot underscore means import everything from math. Okay, that includes the square root, sine, cos, tan, all the mathematical functions. So this is the end result. So this is our standard deviation. Okay, so does it make sense to you? Great. Great. So, all right, let me just give you history. Okay. All right. If you want this particular code also I can give you. All right. Here is right. Standard deviation. And here we go. All right. Great. So is everybody okay, comfortable with this, or you want me to explain a particular step? Or maybe I can just number it. I can just number it for time being. Any questions on this? From step A to I. No questions? Okay. A question from Robin is, what does import math dot underscore does? It basically imports the square root function and other functions from math library, math package. A question from Mohammed is, step G. Okay. Here we are basically calling this is step that you see here. Okay. And all right. So here we are. So this, imagine that we had, okay, so we could actually break it down into something like this. Diff equals this, and then call this. Okay. So this is, now you can see, Sachin, that even though there are so many RDDs that we are creating, this is one RDD, this is another RDD, then, okay, then we computed the sum and count, then, right, then we we created this and so on. All right, a quick question to all of you. How many jobs are there in this approach? Anybody? How many jobs are there in this approach? It actually has two jobs. One, reduce, is an action, and this reduce is an action. Okay, this reduce is an action, this reduce is an action. All right.
So
So
number
when
of jobs equal to number of actions.
that's right.
And one more quick question. If you have a number of chained transformations, the transformation happens from left to right.
Chain, yes, that's right.
So
So
math,
if you look at this one, right? What's happening is this one is returning a new RDD by itself, and that new RDD we're calling with that here. You
math.
can think of it. This one is going to get executed, and then whatever is the outcome here will be basically an RDD, and on that RDD, next function is being called.
All right, got it. Thank you.
Okay. All right. So a question from Sachin is, could you go through it again? What function we apply at each step? So this part we are clear, right? This one is the average that we computed earlier. So that one is a job in itself. Okay. and we are noting down the count. So this one is clear. Next one is here. The same RDD we are taking up again, and using the map, we are subtracting each of these values by average. We are subtracting average from each of these values. Then we are squaring the differences. Okay, this is what we are doing. We are squaring the differences, then calling the reduce on the squares. Whatever is the result here, we're calling the reduce on that. And what is reduce doing? Reduce is basically summing up two values. This is equivalent of saying x plus y, if x and y are two elements. And we can actually convert that into exactly the way we did earlier. And then here we get the sum of square differences. So this part is done. This part is done. Now we are dividing by n and then doing the square root. We are dividing by n and doing the square root. Correct?
One thing,
Yeah.
multiply by one thing is to make the value a double, right? To increase the precision when you do the square root.
That's right. So here what we have done is, in case this sum of square differences is actually number,
An
although it
integer.
should, yeah, integer, then
Okay.
we are multiplying it with 1.0. Okay. Because by default it'll do int by int, although it's not going to happen. Why? Because here initially if we just put a 2.0 here, then everything will be completely okay. Because if these numbers are not, instead of integers, if they are decimals, everything will be completely okay. All right, so that's important part. Now, so that's what we have done. Is math standard installation? Yes, math is a part of the standard library of Scala. Okay, so it's essentially the same library which is there in Java, and they have just repackaged it. All right. Did I miss any question? So it has basically two jobs. One is this. So this is a transformation, right? And this is happening locally, right? And this is again a transformation. This is an action. So there are two actions, and every time you call an action, it will execute a job and give you these local values. All right. So that's what is happening here. All right. So question from Saris is action versus transformation. Yes. So basically the action basically gives you the local values, right? While the transformation gives you another RDD. This is an RDD. All right. This is not a local value. Okay. It's just a step of the graph.
Sorry, one quick question regarding this. So how are you defining a local value again?
Uh, Local value again. Okay. Oh, this I did not know. Who is drawing it? All right. Okay. So you can annotate. All right. Yeah. So we are not defining the local value. When we call reduce, right? It gives you a local value.
Okay.
This is a tuple that's going to be returned by reduce as a local value.
Okay.
All right.
Okay.
So most of the actions, other than say save as text file, other than those, most of these actions give you a local value.
Okay.
All right. So they basically action means telling Spark that, hey, my work is done. Now can you execute everything and give me some output? All right. That's what it means by an action.
Okay, so here like just wanted to
Mm-hmm.
check this once more. So in the bracket, like x dot underscore one, y dot
Mm-hmm.
underscore one, and x dot
Right.
underscore two. So like basically they are returning the square of the values, or
No, this one.
yeah.
Oh, this one is a tuple. Okay, that one I had described earlier. So here, let me just show you that part. I have. Let me just zoom it out. I had actually written it earlier, so that. Okay. Oh, why it's not working? Oh, it crashed. All right. I think it is okay. Okay. So this function that you see here, this is a function that you're talking
Yes.
about, right?
Yes.
Right?
Yes.
So,
Yes.
so yeah, all it is doing is it's summing up the tuples. Remember, it's computing the average. This portion from here to here is
Uh-huh.
actually here to here. If I just indent it a bit, then it'll make more sense to you. Okay.
Okay.
So here to here, we are essentially computing the mean from here to here.
Mm-hmm.
Okay.
Okay. Mm-hmm.
And the same thing that we did earlier. Once we compute the mean, the average, then we are subtracting every value with the mean and squaring it, and then we are summing it up using reduce, and
Okay.
then we are performing the square root and division by n. All
Okay.
right.
Okay.
So this one is clear, right? We are basically summing up tuple. The first value of x, first value of y is being summed up here. Second
Mhm.
value, second element of x, second element of y is summed up here because x and y both are tuple in themselves.
Okay. So what about the
Okay,
other values? So the coordinates. So the I mean, if x y are the coordinates, for the first point. So you
Mhm.
mean to say there are only 2 points, right?
Right.
X1 and X2, Y1 and
X.
Y2.
Yes, yes.
Okay.
So basically, x is what? This value. This one is converting each value into a tuple. Right?
Okay.
Second
Okay.
value is actually 1 initially, and so it'll become 2, 1, 3, 1, 5, 1, 6, 1, total
Okay.
of 4 tuples, each tuple having 2 values. Second value is 1, right?
Okay. Okay.
All right, so I think that will make it okay. All right, great, great. So that was how we computed the standard deviation. A question from Bintao is that could I write one long chain to calculate standard deviation? Of course, you can do that. At least the second part you can do from here till the last, you can do it in a single way. All you have to do is just take the reduce from here, put dot reduce, and then rest of it. You can actually do it in a single shot. All right. Okay. So question from Hitendra is local values are derived by action. That's right. Wonderful. So does it make sense? Should we move on? Okay. So the step B is actually whatever we did in the previous. The slash means that it's a comment. Okay. So the B dot this step, right? This is what you're talking about. The B dot 2.
I did not get it. Reduce. Why it is taking x? I see
Why
only.
stick?
I mean
Yeah.
x dot one plus y dot one. Because in the array we have totally two elements, right? Why it's only two sets of each?
Good question. So it's basically a tuple, not an array. And had it been an array, we could actually access it using the index. Actually, there's a lot of noise coming from your side. I can just
I
correct
can
it.
mute it. I can mute it.
Okay,
Okay.
okay. I'll just explain. So yeah, all right. So we could actually say, imagine that we were having an array, right? Like we had an array of say 2 and 3, right? Then we could actually do x0, right? We could actually do x0 and x1, right? But if we have a tuple, let's say where t is 3, 4, right? This is a tuple, right? So in tuple, we could say we can't say t0, right? We have to say t dot underscore 1, t dot underscore 2. All right. That's why we are using that kind of a syntax. All right. So if we had, let's say, two tuples, let's say T and S is again another tuple, S equals say 5, 6. All right. Then if we have T and S, and we want to sum up these values, what we have to do, t underscore 1 plus s dot underscore 1. This is one of the summations, right? And sorry. Okay. So, and if we are saying the counts t dot underscore 2 plus s dot underscore 2, right? So the t looks like this, s looks like this, and if we are saying the sum and count, this is how it would look like. Sum and count. This is how it look like. All right. Did I make sense here? And that's what is going on here. That it looks little weird, and here this is what is going on. So we are summing up two tuples to make up a single tuple.
So just want to clarify. So if we are summing up three tuples, right? Say
Right.
which is, the last one be z, so it will be x dot 1 plus y dot 1 plus z dot 1, and x
That's
dot
right.
2 plus y dot 2 plus z dot 2.
That. Okay, let me just show you. If we were summing up three, right?
Yes.
Yeah, but see, the thing is, reduce will do that for you. Okay.
Okay.
Reduce will be, if we are summing up, let's say 3 values, so
Right.
it will automatically apply this function 2 at a time.
Oh, okay. Okay.
Okay, so we don't have to worry about the third element. It'll do that for us.
Oh, so we only, the max we specify are 2 in the
2.
function.
Yeah,
Oh.
yeah. So this is specifically for reduce functions, the function that we're passing to reduce, because reduce takes an element, reduce take a function which operate on two things at a time. And
Yes.
what it does is it is going to repeatedly call your function such that it is going to repeatedly call your function again and again on the values to give you a singular value.
Okay. Okay.
All right. So
So
that's what.
the computation is done by reduce basically.
Yes. Your
And
function is going to be called by reduce.
and then RDD is doing the design part.
Right.
Okay.
So reduce is operating on RDD.
Right. Right.
Okay. Great. Great. All right. Wonderful set of questions. Is there a function in Scala which avoids these steps and directly computes standard deviation? There is no function Scala, but there is in Scala, there would be a function as part of math, but that would be doing everything locally. But there is definitely a function in MLlib of Spark, which does exactly same thing. All right. Which does same thing in using in the library of Spark. So we learned that even the basic things like average and standard deviation and everything has to be modified. Therefore, it's important to understand that the libraries like MLlib have been rewritten from the scratch. They are basically machine learning library. Machine learning libraries are nothing but the algorithms applied on the data to do the predictions. And those libraries, there are libraries available that run locally, but Spark team has rewritten most of the functions so that they can work, they can take the advantage of distributedness of Spark. So that is the difference that you will face. There's another question that people ask, that why do we have MLlib when we already have so many other libraries? The MLlib of Spark is designed exactly for this reason, that it is designed for distributedness. It is designed to take the advantage or utilize the network in order to make our computation faster and on humongous data.
One quick question. Sorry, if you go back to the previous slide, the RDD part. So, for example, if here, if there were like three tuplets, so how would you define the RDD the same way? The underscore minus.
We have defined here. You can see the step number 1. We are saying as c dot parallelize, and there are 4 elements.
Right.
Okay. There are 4 elements, and it's basically this RDD count is actually having 4 tuples.
Okay.
Okay.
And so what is this 1 standing for?
Yeah. every element is being converted into a tuple, right?
Right.
So
Right.
actual value is becoming the first member, and the second value is 1. So
Okay.
if you take a look at the here, if you say RDD count, right?
Right.
RDD
Right.
count and
Right.
say collect, right? You could
Correct.
take,
Yes.
yeah, you could see it has how many elements? It has 4 elements. Each
Okay.
element is a tuple. 2, 1, 3, 1, 5, 1, and 6, 1. All
Okay. So the
right?
y coordinates are all 1 here, right?
Correct, correct.
And so if the y coordinate was 3, so we could have put like 3 here in the RDD map in the brackets, correct?
That's right.
Okay.
That's
Okay.
right. So this is exactly what we're doing. I'll just go back. This, you see the diagram?
Right.
Imagine that we had 4, 5, 6. We're
Right.
putting 1 with each
Right.
one, and then
Right.
we are summing it up. All right?
Right. Right. So my
So
one
this
question
function,
here is the one is constant here, right? For all the tuplets. But if the one
correct,
varies, say it's 1 4 1 and then 5 2, then 6
right,
4. So how
right.
does it work then? Yeah.
Yeah, it'll work in the same way. But my
Okay.
question is, here, what is it that we are trying to do? We are trying to count and total
Right.
both together. Correct?
Right. Right.
So since we have given 1 1 to each,
Right.
if we have to count a number of people, right?
Right.
And instead of counting that way, we just give them all, make them an array of ones, and then sum it up. Then also we'll get the same answer, right?
Right.
So
Right.
what we are doing is we are putting 1 on each and letting it sum up till the end.
Okay. So we are basically fragmenting it apart.
Yes,
Okay.
correct.
Okay.
Okay. So
Thank you.
we are converting each element into a tuple in the first go. Okay. And then we are summing up the total and we are summing up the counts. Initially, we are saying that, okay, 4 means 4 is the sum of this value and 1 is the count of this value. 5 is the sum of this value and 1 is the count. So, and so on, right? So that's what is going on. All right, so that's about the computing average, and after that we've utilized the same technique to compute the standard deviation. Okay. A question from Robin is, which programming language did Spark use for standard deviation computation? They used Scala. All right, they used Scala for doing that. All right, the whole MLlib is written in Scala because Scala is the fastest choice of the language, and it's just slightly slower than C++, but it is faster than Java, and Java is faster than Python and other languages. So you can say that out of the advanced languages, Scala would be the fastest. And I mean, actually, the frameworks are generally written in C++ still. For example, TensorFlow is written in C++ to take the advantage because it is extremely fast and runs on the local machine, and so on. So, okay. A question from Stories is there any flexibility of fragmenting to 2? It's up to you, all right? So it's up to you. And I'm not why. So we are not really fragmenting it. If you take a look at this, why we are there is a purpose that we are doing putting 1. Why we are doing that? Because we want to do the count and summation in a single shot. All right, because computation of average was wrong. Therefore, wrong because we could not use reduce with it. Therefore, we used this kind of a technique where we did the computation of summation and counts together, and therefore we put 1. And it is up to us if our values of tuples were 4 and 2, 5 and 6 and so on. We can actually do whatever we want there. All right, so it is definitely flexible. It's going to sum up both of them. All right, it's going to basically sum up whatever way it is. All right. So here you can, yeah, whatever is the tuple, it's going to sum it up that way. All right. A question from Raju is the better part of using a question from how Spark is better than MapReduce, better performance of using Spark instead of MapReduce in cases like, okay, all right. A question from Raju is that how the Spark is better than MapReduce, the Hadoop's MapReduce. A quick answer would be that this one is far more performant, and this one is far more performant. Spark is far more performant, and it's easier to program with Spark. As you can see that whatever we are doing is actually happening on Spark, and we don't need to really maintain a project for the class, right? That means that I can just write like word count problems right away without having to copy paste from here and there. That essentially shows that it is really simple and quick to code for Spark as compared to the MapReduce of Hadoop. All right. So programming model is better in case of Spark, as well as the performance is far better in case of Spark. The only difference is the only point where the Hadoop would basically do better is because if the data is really humongous, in those cases Hadoop might do a little better, right? So the reason is the design of the design choice of MapReduce were on the scale of Google, while the design of Spark was more practical with more practical assumptions of data. A question from Rajan is this: in this example, assuming here are 3 partitions, can you explain which step is executing in partition and which is local? All right. So all the action, the things like this, average is happening locally. Okay. So actually we can, and take a look at the code and then it'll make sense. All right. Okay. Yeah. So this is happening locally while the reduce is happening over the cluster. Okay, over the cluster. And reduce, actually the way it would happen is the way we described earlier. And then okay, so the way we have described earlier, you can think of it in this way. If you go back here, right? I'll have to go back. Yeah, this one could help you understand. So when we are calling reduce, some of the reduces would happen on each partitions, and some of the reduces will happen on the driver. Okay, the same function, whatever you're calling, could happen this way. Okay, you can actually express the entire logic in the same graph way and would be able to visualize it. All right. So coming back to where we were now, here. So you see that here, what we are trying to do is this part is local, definitely, because it doesn't involve any RDD. This is a local variable. This is local variable. You can try typing these values. Let's say you want to check whether sum was a local variable or not. You can just say sum. You can just say count, and you can just say RDD count. You can see it's an RDD. So you can quickly take a look at all the variables here, and you'll be able to figure out which variable is of what kind. Like for example, sum of square differences. All right. Here and so on. Okay, you could take a look at all of these. A question from Bintao. Spark can work in R, Python, Scala. That's right. Is it possible for you to show us the code for them respectively while you're focusing on Scala. So I can definitely show you in say Python right now. Okay, but the R1 I'll take to do, because the R1 is a bit different. So we'll talk about that after Spark SQL. All right. Thank you, Bintao. Thank you for doing that. So yes, this one is good. And PySpark, you can use. I think you can convert it. So no worries. All right.
And the map function also will work on the Spark side. Map.
Yeah. Yeah. This map is actually happening on Spark only.
Okay. So it is not happening locally.
You know, this RDD is a Spark variable. It's not a Scala collection.
Okay. Okay.
Okay. So the moment you say parallelize, it became an RDD. And RDD, because we are using sc.parallelize, we are saying Spark context dot parallelize, so it creates a RDD for us instead of local collection. Had it been like we were using array or list or some other construct from Scala, then also actually everything will work fine. If we actually missed, let's say, saying sc.parallelize for time being, like, so if we missed saying sc.parallelize, actually the entire thing will work fine, and you will think that we did everything in Spark, but it's actually everything is happening in Scala. All right, let me just try if it works. Yeah, that's an interesting observation. So right, so you can actually so let's say I forgot to say sc.parallelize here. Okay. Okay. All right. So let me see. sc.parallelize. Sc means Spark context. That's the entry point to Spark. See, that's the interesting part. So the entire project is working perfectly fine, and it, instead of being happening on the Spark, is happening locally. So this is a little confusing part, that people would think, oh, I'm using the Spark here, but you're not using Spark at all. You can actually run it without even Spark. You can actually run it on Scala prompt. Okay, you can actually run it on just Scala. I'm running right now only Scala, not Spark Shell, and it is still running fine. All right. I hope you got the difference.
Yes. Yeah.
All right. So basically, the sc.parallelize converts it into RDD, which you can do that.
Sandeep, why I'm
Yeah.
getting error when I say sc.parallelize?
Did you launch this using Spark Shell, Spark dash shell?
I don't think so.
Okay. So Scala doesn't have SC, and that's exactly the difference between Scala and Spark Shell command. These two commands.
Okay, I got it.
All right. Great. Great. All right. So that's pretty much for today. And yeah, this was an interesting observation, that actually the whole code would work fine, perfectly, without even knowing that it's running locally. All right. All right. So that's pretty much for today. There are some questions which Mohammed is having. If you want to stay back, you can stay back to participate in the questions. And we will continue from computing, solving a couple of more problems with Spark, and making ourselves comfortable with this way of programming. All right.
Sandeep, how many classes or more are there?
At least 6 to 7 would be there.
Okay. Okay.
All right. Yeah.
Sandeep, just one question.
Yes, Alok.
Yeah, like a general question, like once the course is completed,
Yes.
so whatever in our course list, that videos and the things, so
Right.
should be there, or it will be not be there?
It will be there for all of you, and
Oh,
we will try, as long as the company is surviving, we will keep it up. If if the company is shutting down, then we will let you know that you can download it or use it. All right.
okay, okay. Thank you, Sandeep.
Okay. Yeah. A question from Binta: is there a comprehensive project coming up to us soon? Yes. Okay, let me just make a note of this point as well. Okay.
Sunny, one thing, like, do you have like 1 minute, 2 minute? Like,
Yes, yes, go ahead.
so like I came to one idea in my mind. Like, I want to make some kind of project or product.
Mm-hmm.
So like we have like big shopping mall. So from there, if we have like the people usually like tendency, the people will purchase one thing and
Mm-hmm.
they will purchase other things with that things what they are purchasing. Like suppose
Right,
the who is smoking, that they definitely take, somebody take the ice cream or somebody take the cold drink.
right,
So this kind of traditions we have seen so many places.
right.
So if we have that kind of transactions data, like the
Mm-hmm.
pairing of the transactions, like this things he has purchased, he might be purchased this because he already purchased. So
Right,
if we have that transaction data and we can recommend the like the community, like big shopping mall, like okay, your stock is getting low, so you can purchase more because this is getting down your stock, and so this also getting down, so you can purchase it more or make it like stock management kind of things.
right, 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 right.
So what should be the approach of doing that? Like
Okay.
mlib kind that you have told earlier, we are like mlib like machine learning kind of things, so we
Right,
can
right,
get the
right, right,
recommendation.
right,
So
right.
what kind of format we have to create the input, means
Okay, okay,
the
okay.
data
So,
structure?
yeah, I would actually recommend to you that take a look at the
Okay.
MLlib. It actually covers exactly the same problem that you're discussing. All right.
Okay.
So it basically goes through there is a problem statement of recommendation generation.
Okay.
Since the data there, we don't have the e-commerce data, we use the movie lens data that you have watched this movie. You may also like to watch this movie.
Okay.
Okay. And that's the kind of project that we deal with. It's actually extremely simple and straightforward. All you have to do is load the data from text file using sc.text file,
Okay.
convert that into an RDD by expressing this, and then from RDD we convert it into data frame, which is again converting RDD into a table, and then feed it to the algorithm, and algorithm gives us the results. All
But
right.
before that, into the file, we have to make the pairing, like this this
Yes.
this
Yes.
item we have purchased. So what are the probability of purchasing the other item? What already this kind of tradition is going on. The
Right.
people
Right.
is smoking, they will get the like cold drink. This is bad example, but that is the tradition kind of things.
Mhm.
So this pairing we have to create, and then we have to process the data.
So what we have to do is see the thing that I actually did at say in Mobi or even at a couple of times, it was in the same lines, and main time would go in preparing this data. What you're suggesting.
Yes.
Okay. Main time will go in basically preparing that this person bought this, also bought this, and also bought that. This person, this second person bought this cold drink, then this bought this and this. So preparing this historical data is all it takes to actually solve the problem. Rest of machine learning library, it just really breeze. You just create once you have product. So instead of let's say saying that like the way I'll explain again, it's very simple idea. So I hope it will finish in like 1 or 2 minutes. So
Or we can get the data from that shopping mall. They can give us all the billing what they have did for last 2 years for all the transactions, so we can get, okay, this person has purchased this many things,
right,
that
right.
person purchased
So
the
so
similar
the way
kind of things. Yes.
Yeah, yeah. So the way we generally prepare is in this way that Alok bought, say, let's say Alok bought an iPhone, right? And then Alok also bought some other things like
Phones,
uh,
headphones.
headphones, right?
Yeah.
And now let's say uh, Alvin has also bought an iPhone, and there are more people who buy a particular headphone just by this. So all you have to do is prepare this data and feed it to MLlib, and MLlib will basically suggest that Alvin might buy headphone with this much probability. Okay, so here you have to write down that Alok uh, Alok bought iPhone, and what is the, and or Alok liked iPhone this much. So, and Alok also liked headphone. So generally what happens is preparing this data is the hardest part. So instead you come up with this technique saying, okay, if Alok put the headphone in their cart, we say that probability of their buying or their preferences is say 0.3. If say Alvin has put the iPhone and went bought it right, I mean, instead of buying it, let's say uh, he basically visited a particular iPhone page like 100 times in last 2 weeks, we say that the probability of buying is this. So basically the data that we prepare is how much Alok likes iPhone. Okay,
Yes.
and then we feed it, and then we prepare the outcome is how much Alvin will like to buy headphone, how much will is the probability. So we basically prepare this out of 5. Okay,
Yeah.
out of 5, like that. All right,
Hi Sandeep, can I go ahead?
yes, go ahead please.
Yeah, so I'm trying to I want to design like a Spark streaming application.
Okay,
So what would be a good starting point? Because last time when we spoke, you
all right,
said like cover Zookeeper, cover Kafka, cover HDFS.
right,
Those
right.
things I'm done
Yeah,
from my courses. So now I just want to
awesome.
start with Spark streaming. So what would be a
Yeah,
good data set to do it, and what would be a
so
good starting project?
Spark, yeah. So this one is the most popular project that we have online. All right. So I would say I would strongly recommend that just go through this one. That would clear all your doubts. And this one actually is a practical project that we did for Dell. And right. So the story is that Abhinav was basically one of my student, and he worked on this project from Dell, and then he joined my team, my core team. Okay, so basically we did this for Dell, and I would start here, and if yeah, that actually covers entire thing. It covers entire thing, setting up the dashboard and everything.
So this is using the Spark streaming library, right?
Yeah, yeah.
And using any machine learning as well in it, or just Spark streaming?
Yeah, it is not, but here at this point, when you're pushing the data from Kafka to here, or at this point, you could use machine learning library.
All right, so this would be like a basic project to start off with.
Yeah,
This would be
this
like,
would be a basic project.
can you put
Yeah.
that in the link, please? Oh, you put it already?
All right. Yeah.
Yeah, I have it. All right, thank
Okay.
you.
So even yeah, even you can actually search for Spark streaming dashboard. Okay. So we generally come in the number 1. All right.
Okay, oh, wow.
Okay.
Actually, I saw another blog post which was like it talked about Twitter data.
Okay. Okay.
And I think the application was word count. It was on the
Okay.
blog. It was on your blog only. That's what I'm
Okay.
saying. I think that
Okay.
was
Okay.
regarding word count. So they had some tweets coming in
Right,
real
right, right, right,
time.
right.
You
That
know,
was Hive project. That is Hive project, but you can actually do it using actually the one of the projects that one of the last intern that we had from I think UC Berkeley, what he did was uh, instead of he used for the project that we have, the Hive project that we have, he converted that he did that using Stanford NLP, okay, and Spark streaming. uh, he basically converted that project into this. but I'm not sure where is that project. He has not published it yet, but you can give it a shot. It's not that hard, and I can support you there. All right.
But I'll just start off with the one that you said earlier. In
Right.
case I have questions, I can just write.
Right. So here, what we have done is, as part of this project will guide you through the entire process. And
Okay.
at the end of it, you'll get the entire picture, because the problem with these streaming projects is getting the picture, because there are just too many moving parts. Okay. So the actual work is tiny while the assembling is harder. Okay. That's why it's important to get the assembly done, and then you can individually improve the parts or change the various inputs and outputs.
I didn't get that. Can you say that one more time?
Yeah. So see, this assembly, once you're done with it and you're happy that, okay, here when I pump the data here, I'm getting the dashboards,
All
right?
right.
Now, if you keep the same approach and same, the workflow remains same, you just change the data to Twitter stream,
Okay.
change the Spark streaming's logic, and rest of the things will almost remain the same. Okay.
All right.
So
So
you can actually, yeah.
once your architecture is ready, you simply change the data set.
Yes. Change the data set, tweak your code in order to fit into the new need, or change the logic here, put the more machine learning libraries, or put some other third-party API calls or whatever. All right.
But I would just request to have like at least 2 projects in the course, because it would
Yeah.
really if it's hands-on.
Yeah. So it is going to be, yeah. So I think I'm going to put more projects. So there is all, yeah. Yeah, we have actually one project at the end and one project in MLlib. So those are the 2 projects. And Spark Streaming, again, it is a project in itself, the one that we're going to. So these are 3 separate projects we have here, and maybe we can just put more projects separately for everyone. So let me just review what all project can we do. Okay, so let
Today
me
in
just,
class, you spoke about that image resizing, I think.
yeah, that's
So
my to-do
that,
list, you can see here.
so, all
Okay,
right.
yeah,
That's in the next class that we're going to aim at.
yeah, I'm trying to do that, yeah.
All right.
Okay, so all right, so if you guys have something and you want to take it up, I would love to do that. Yes, Binda, you can take it up, this particular project, and this in itself it's a good project to do. All right. So yes, actually that is something that I always forget to mention. So I think all of you can give it a shot, this one. The reason why I'm not talking about it right now is I'm waiting for the Spark streaming to finish, and then I can talk
All
about it.
right. Okay.
All right, great. So yeah, so is anybody else is having question?
Thank you,
So,
Sandeep.
Sandeep, which is the current project we can do in my courses? Or
My course is right now there is actually you can yeah, I think you can try this now. You are ready for this. So actually the last project that we are going to do, okay, the last project that we're going to do, you can actually try it right away. It's going to be pretty simple for you now. Whatever we have learned so far, okay, that you can actually try now. Yeah. So here, if you go to say, here, let me just wait. All right. So we have this, specifically this one. Okay, this is actually a pretty simple project. You can actually do it right away. Okay. Or if you are getting stuck, just wait for the time, and at least the first problems. Okay. All right. I think let's just wait for one more session. Okay, then you can attempt this. You can attempt this project after one more session.
so you are uploading more projects. Yes.
But yeah, so this we will do the next one after next session. Okay, and then the final project you can take it up like the dashboard one, the dashboard that we talked about. Okay, the one, this one. Okay, this will be, you can take it up like a final project, this one. And the next project, let me I'll be adding more projects to it, although we have like 4 or 5 projects in this course. There are around 4 or 5 projects in this course, just that since we are beginning with the things, that's why we are avoiding. Can we mute? There is a sound coming from the background. All right, so yes, so we'll be adding more projects. So right after next session you can attempt this project. Okay, after next session. Any other questions do we have? All right, so somebody is saying okay. All right, a question from Binta is, I can do it in PySpark. Yes, please go ahead. Okay, yes, please go ahead. If you are comfortable with PySpark, then you can just go ahead with PySpark. I'm completely okay with that approach. All right. It's about Spark, not Scala or Python. It's about understanding distributed computing. All right. So those of you who want to continue with Python, they can continue with Python. I would love to support you, don't worry. And all right, is there any question that all right, no, so question from Sari is it on the verge of closing down? Not really, not really. We are doing good. CloudxLab is doing good, and we have a good faith of our students. And so, all right. So it's basically a lot of our students are actually referring each other, and therefore we there's no worry of anything. All right, great. Feel free to write on Quora or feel free to refer your friends, and that will be great. All right, wonderful to have all of you in the session. Every session is equal amount of learning to me as it is to you, and every question is in itself is very important, and that helps us grow together. All right, so thank you everyone. I look forward to see you next week. Bye bye, have a good day. Thank you, Robin.